Best things dwell out of sight, wrote Emily Dickinson in her brilliant poem. Today, I will introduce a model-free method to see things that are usually out of sight. By see, I mean recover in real space information in the atomic length and time scales of multiple motions, a molecular movie beyond what is traditionally resolved. Molecular movies are mostly not observed in real space. A molecular movie is simply optical pumping and then X-ray scattering probing of a non-periodic sample, for example, molecule in gas or in solution. This was demonstrated in a seminal experiment by Miniti and Weber on the photophysics of cyclohexadiene in the gas phase. This molecule was excited by UV pulse, then probed after some delay with an X-ray pulse. And often the data of the scattering is integrated over angle for better fidelity. Now, to understand what's going on, the scattering data alone is not sufficient. Modeling and sorting of molecular trajectories is usually used, as in this case, where out of numerous trajectories, 3 that best fitted the scattering data were obtained and added together. They are seen in these color lines over the experimental black lines for different time delays. This approach is model dependent and usually limited to specific excitation pathway, and we don't see things in real space. Now, to understand the challenge, why can't we just transform the scattering information to real space? We need to start with a simple example. First, using scattering in typical conditions, we have a Fourier relation between the charge density and the scattering pattern. This is as a function of the scattering angle or the photon momentum transfer vector that we'll use Q. Because samples we discuss are non-periodic, the information from the scattering pattern is limited to the distance between the pairs of charges, or the pair density. So we'll do the same. We'll simplify by averaging over all angles and discuss only the isotropic scattering part. This captures still all the dynamics. And we can further simplify and assume only a single type of pair density. The scattering information out of that is made of 2 parts. The first part is the atomic form factor, which is time independent and can be subtracted in pump probe experiments. The second part is the molecular scattering, which contains the information about the pair distance in real space. So here's the example. Assume we have a diatomic molecule where the distance between the atom pair is exactly 2 angstrom, and we're presented with the Dirac delta function. Super simple. This expression below transformed the real space distance to the reciprocal space, to Q, where we obtain the scattering curve as 0 in the expression below. Now, in reality, we don't measure an infinite Q range. We're limited by the photon energy and the detector size. And so the scattering signal is truncated below and above some limit. Here we truncated above around typical values of X-ray free electron experiments where the signal is limited between 0.5 and 4 inverse angstrom. By multiplying the scattering signal with this window function, we apply, in essence, the measurement constraint. And this constraints can take a more general form, as shown here, to include detector discretization, Q blur due to sample thickness and distance from the detector, as well as Q-dependent signal absorption and additional additive backgrounds. The challenge is now to obtain the real space information. And by inverse transforming back to real space, we see how the pair distance as 2 angstrom is completely obscured. And this has to do with the way the window function transforms back to real space and generate these main lobes, as well as we have limited resolution because of the truncation of the Q range. The way to address this challenge is actually displayed now in front of us, as we just described how a pure mathematical signal, a delta function, gets distorted in real space due to the measurement process. We can use this approach to generate a scattering kernel, a function that describes that distortion that naturally arises from the measurement and the analysis. Just as in the example we just saw, where a kernel for the 2 angstrom generates a pair density waveform that is distorted as shown. Now we can form a dictionary of these kernels, sampling endpoints along a range of distances, for example, from 0.1 to 20 angstroms, where each kernel waveform is composed of points given by the detector discretization and analysis. This is how such a dictionary looks like for the example given before. The challenge now will be to use it to express the measured signal under the measurement constraints. But let's go beyond a delta function. Let's demonstrate this on a system that exhibits multiple types of complex wave packet motion in real space, such as this excited wave packet in the atomic iodine that is far beyond a delta function charge density source. We solve the time-dependent Schrödinger equation for this system, and we subtract the unexcited part and obtain our so-called ground truth movie, or dissociation and vibration, as well as ground state depletion observed. We use this ground truth and simulate the scattering signal. We add noise, we apply the measurement constraint by discretization and truncation to the 0.5 to 4 inverse angstrom range as before. We inverse transform to real space and see how the limited Q range restricts the way we can interpret the inversion. Now, we'd like to represent this distorted real space inversion in a linear model in terms of that dictionary that is composed of the scattering kernels, and how much each kernel contributes given a weight vector, W. One could attempt to solve this model using least square minimization. However, this approach is sensitive to noise and is generally unstable numerically when the problem is ill-posed. A standard approach for solving this inverse problem is to use regularization framework to promote solution that has properties based on information that we have from the data. For example, a widely used regularization approach that addresses the numerical instability is the L2 norm regularization, where we add the sum of squares of the weight vector to the minimization. And lambda is a coefficient that controls the magnitude of that term. This approach has an analytic solution, and we can observe how it reduces some of the artifacts of the inversion. While this regularization promotes solutions that are stable and smooth, it also generates some artifacts, as it promotes most of the weight vector components to have non-zero values. This may reduce the ability to interpret such solutions, especially for the case of weaker signals that may be present. For the case that the scattering signal is sparse, I mean that just a small number of sampling points in R can explain the distorted real space inversion, smaller than the dimension of the total R signal. We can use the L1 norm regularized least square model, where we use sum of absolute values instead of the sum of squares. Now, while there is no analytical solution for this problem, it can be solved using convex optimization. This approach not only accurately captures the real space position and motions, but also manages to recover and even super-resolve details in the dynamics, such as wave packet dispersion, while almost eliminate noise from unrelated distances. Because most of the sampling points used in real space in R at any given time have no charge density or no motion signal, the approach illustrates the justification of the sparsity assumption for diffuse scattering signals, where relatively a small number of positions in R play a role. The recovery accuracy and resolution are expected to be limited when two or more pair distances start to overlap in the presence of noise. We model this using a triatomic molecule, such as CO2, where we fix the position of the outer atoms while changing the position of the central atom. When the central atom is exactly at the center, the pair distances to the two other atoms will overlap. We model the scattering from such a case with the same measurement constraints as before, where we expect to have a resolution of 1.6 angstrom. This is the 2 pi over the maximum Q range. We then test the recovery for a range of signal-to-noise ratios with 20 realizations for each noise level to obtain recovery statistics, and the results are compared with the true positions marked in this dashed red line. We can observe that the recovery accuracy is proportional to the noise level, and in that sense, it is gracefully failing for increasing noise, demonstrating the stability of the approach. For the case of the separated pair, the two outer atoms, the recovery area is less than 0.1 angstrom across the signal-to-noise ratios, demonstrating the accuracy of the approach. Here, the line of that plot is the average error, and the shaded area is the standard deviation from the 20 realizations. Now, for the case of the pairs that starts to overlap, we showed the average accuracy error in this color map as function of the noise level and the distance between the pairs. For the two pair distances around the overlap point, we observed that depending on the noise level, there is a minimum separation distance of about 0.3 angstroms, below which the solutions drift towards the overlap point with a recovery error of about 0.2 angstroms. Overall, the resolution depends on the fidelity or the noise level, and we can see that across the noise range, the accuracy is always better than 0.35 angstroms. This approach is easily extended to the case where there is more than one type of atomic pairs that contribute to the scattering signals, using an approximation to the form factors that is discussed in the paper. For ground truth here, I demonstrated using a trajectory calculation of the direct dissociation dynamics of CH2I2. We have now iodine-iodine and carbon-iodine pair distances, and we can simulate the scattering signal for the same range of values that is reported in the experiment. We can add noise, and the inversion of that is seen in the middle figure. Now, using the natural scattering kernels approach, we can recover in real space the motions of the different pair density distances. And note that we can see also the signal strengths. The iodine-iodine pair density signal is 10 times stronger than the carbon-iodine pair. Finally, here are preliminary results on experimental data of an even more complex system. Here we measure scattering in iridium diamond, a 130 atom model photocatalyst system in solution. The iridium atoms are strongly scattering and they act as contrast agents for the pair densities. We also use here the natural scattering kernels and recover in real space multiple motions, and we can even disentangle intramolecular structural dynamics from the contributions of the environment around it. This work was supported by the US Department of Energy, Office of Science, Basic Energy Sciences. If you have any questions, feel free to contact me online or offline using my email, and use the QR code for more information about this work and other from my group. Thank you.